cover today is still examiner. So that will be part of your exam topic. So it's about the momentum method or impulse and momentum method for the rigid body. Give me a second. Okay, let's go to the subject. Okay, you may view this. Okay. Okay, we did cover the energy method already, and then now we're going to talk about momentum methods, impulse and momentum. So, what is the concept about the momentum? Okay. So I'll take the example of this Chappi tester. Okay, and then also, okay, let's see. Okay, Chappi tester is basically a pendulum that swing to hit the sample. Okay. So in this case, why is it important? It's because it has the speed and impulse that eventually will break some sample. Okay, let's see. So view the video. Okay, we'll see this. That's the short one.
The Charpy Impact Test. The standardized Charpy Impact Test has been designed to measure the toughness of materials under impact loading and multi-axial stress state. A pendulum impact testing machine is used to do so. The pendulum on the machine has a heavy weight at the end. This is lifted into the starting position in step 1. Then the tester checks whether the testing machine has been adjusted accurately. In order to do this, he turns the drag indicator downwards and releases the pendulum without a test specimen. The drag indicator stops at position 0. This proves that the pendulum has the correct starting position and that the friction is correctly compensated. The machine is ready for the tests. First test, strain-aged plain carbon steel S235. This is our test specimen. It has been machined to standardized size and shape with the characteristic V-shaped notch. The tester places the specimen on a support in the lower part of the machine and adjusts its position with a centering device. Next, he turns the drag indicator downwards again and checks that everything is prepared correctly. Perfect. The test can begin. The pendulum is released, it swings downwards and hits the specimen with its rounded hammer P. The specimen absorbs part of the pendulum's energy, so the pendulum doesn't reach the full height on the other side. The amount of energy that has been absorbed by the specimen can now be read off at the position of the drag indicator. It only amounts to 13 joules in this test. Here is the main principle of the measurement. In its starting position, the pendulum only has potential energy. It is given by mass of the hammer m times gravitational acceleration g times starting height capital H. After the pendulum has been released, the hammer moves downwards, hits the specimen and then only swings to height small h. Exactly at the first reversal point, the pendulum again only has potential energy, which is m times g times small h. The energy that has been absorbed by the specimen is called notch impact energy, kV. It corresponds to the difference between the two potential energies. The first specimen only shows very little plastic deformation. A mostly flat, slightly glittering fracture surface has been formed. This is another important indication that this kind of steel is only able to absorb small amounts of notch impact energy. It shows mainly brittle behavior due to the strain aging effect. Second test. The second specimen has been made from normal.
Okay, so after seeing this, okay, then next comes the point. Okay, so how does this hammer manage to break the sample? Okay, so in this case, so you can say that it is the potential energy, okay, of the hammer, okay, that changed to the kinetic energy. So when the hammer comes down to the lowest position, so this will give you the gain in kinetic energy. Okay. So what you see here is the high edge of the hammer. When hammer reaches this position, okay, it is gaining in speed. Okay, right before hitting the sample. Okay. So once the sample, like for example, the one with the notch is broken, okay, so this sample isn't resistant, okay, to the impact, okay, and then here you don't have any because the material is mounted, so there are no rebound, okay. They are not the rebound of the two particles, but this present resistance. Okay, when this hammer got to go through this material over a distance, let's say d, then the work done by the resistance, okay, yeah, is the energy loss. So as a result, you can see here, after the impact, if the hammer come rising to this position, okay, so you can see that the height is lesser, okay, as compared to the bottommost positions. So eventually you got to minus the energy loss, okay, and that is going to become potential energy again, okay. So after the impact, so the speed is already getting lesser, okay. So this speed is lesser, okay. This kinetic energy is lesser after the impact, okay. So conversions is then going back to the mgh, okay. Okay, next we also study about the momentum due to the injections of this engine. Okay. So if one of the engine fail, okay, then there will be a rotation. Okay. So how to describe this angular motion using momentum? Okay. So I would like to introduce you the concept of linear momentum first. Okay. If you now have a mass, it starts from horizontal position. If you look at it as a planar rotations, okay, it's rotation on a plane, on the frictionless platform. You can see this change in the angle, change in the angular speed, and change in the angular acceleration. Then the distance traveled here is s. The velocity along the circumference is L theta dot. The acceleration along the circumference, okay, we put it the tangential acceleration, then that is L theta double dot. Okay, that happens over the instantaneous time. Okay? If now this rotation is due to a circumferential force, okay, then you can write Newton's law. Circumferential force is causing that mass to undergo the circumferential acceleration. Okay, this is what you learned before. And you also know that if you do the time integration of both, okay, if you do the time integration of both, f dt is equal to a dt. F dt is then your impulse, okay, along the circumference. And then this one will become the tangential speed difference times the mass. So this is what you learn as the linear momentum change, okay, as a result of impact. Okay, so in a way you can write this is the starting momentum is going to plus the impulse is giving you a new momentum. Okay, so this is what you learn about the linear momentum. Okay. Okay, and then next, we're going to study about the angular momentum. Okay, how do we extend the idea of linear momentum to angular momentum? We can start from the equations. Okay, if you look at the same rotating mass going through a circular path, okay? So easily you can write this. Okay, previously we write F equal to MAT, okay, to describe the tangential or circumferential accelerations. Okay? Now remember, you can also write by multiplying the radius. Okay? So in this case you are viewing from this axis of rotation O. Then this one you can write MATR. And you recall what is your tangential acceleration. Okay, rather than writing L, I now define this distance as R. Okay, they are equivalently. Then you can write R angular acceleration. Okay, if you now do the substitution back, okay, then you have a concept. In this case, what you have here is MO, there's a moment about the axis of rotation. This one becomes mr squared equal double dot, and this expression is basically the moment inertia about O times angular accelerations. Okay? If you now do the integration of the moment with respect to time, on the right hand side, then you have the integration of angular accelerations. So what you have here, you define this angular momentum as a chain of these angular speed. 所以同学看到没有？所以你们在定义角惯量的时候，跟线性这个角动量跟线性动量，它的概念是差不多一样。OK， 它本来就是同一个圆，只不过说这个时候，你的式子就写成这样。Okay, this got some issue. Am I writing the right equation? Okay. So this is a simple extension, but the actual thing is not that easy. Okay? If you now look at the same thing, but drawing these with the square. Okay, my question here is, are they self-rotation? OK， 同学看到没有？如果我刚才是画圆形的，我代表的是一个点质量。OK， 那如果我现在把圆形画成方形，哎，你有没有发现这个公式好像有点怪怪的？ OK， 哎，请问一下，如果我拿着黑板擦做转动 ，OK， 各位，黑板擦在手上转，请问这个黑板擦有在做自转吗？它除了做公转 ，OK， 来擦黑板，你这个黑板擦有 公转自转 ，OK， 什么叫公转？黑板擦绕着我的肩膀在转，这个叫公转。那请问黑板擦有没有自转？这样是绕着什么转？以我的手为例，我在擦黑板。 OK， 对，差不多绕着手掌或者二手吧。OK， 所以你看到没有 ？So in the case here, if you recall what you learned about the MO, if your moment is a rotation about the axis of rotation, it's going to be equal to what? It's going to be IG omega. This is what you call self-rotation. Okay? And second, you're going to write your MAT. That is your tangential acceleration times the mass times the moment arm. Okay? In the case of the point mass, in this case, you are talking about the particle mass, okay, which has the self-rotation. Okay? You remember how you define Ig? It is your nk squared. K is the radius of gyration. Okay, and k value is nearly 0. Okay, but in the case here, okay, it's not 0 because if this is a square or this is a tube, Ig is nk squared. It is not 0. Okay, what you had previously here, to be honest, you are not talking about the self-rotation part. You are talking about these NATR. 所以刚才我推的这个例子，它是假定 k 值等于0，所以是这一项没有出现。那第二项是什么 ？NATR. Okay? So you are not sure, then we do the integration. If you do the integration here, then I can rewrite the expressions. Okay, you see here, if I now do the integration, this is going to be Ig omega dt plus NATR dt. Okay? So the left hand side is the angular momentum, right hand side is Ig. Okay, sorry, this should be written as alpha. This is angular acceleration. Then you integrate the Ig, angular speed 2 minus angular speed 1 plus radius times mass velocity 2 minus velocity 1。OK， 那同学，你是看这个例子，好像觉得有点不大一样，但实际上它是一致的，只不过是说这个是自转。造成的这个 angular momentum change。我这边呢，它这个是公转 ，OK。So in this case, now you can see what this is. If you are not doing any self-rotation, I draw this. This is the starting posture. So this is the posture at 45 degrees. And then this is the posture at 90 degrees. What is your self-rotation? Your self-rotation already undergo 90 degrees after you come to the top. Okay? It was 45 degrees when it was halfway of a quarter. Okay? 好，同学看到没有？所以这个就是你们要有的一个既有的概念。好 ，after this, now we come to the example, so you can have a clearer idea. Okay, if you have translations, you only have linear momentum, zero angular momentum. Okay? Okay, if you now have the rotation about a fixed axis, okay? If the axis of rotation is away from the gravity center, then you can still define a linear momentum at the gravity center, and also the angular momentum at the gravity center. Okay, however, if you want to find the angular momentum about the axis of rotation, then you have to do the sum of the two. The first part coming from the self-rotations, the second part coming from the translation. So this is how you define the angular momentum about an axis of rotation. Okay? And then for a general motion, okay, you don't have a fixed axis of rotation. But not to forget, you have an instantaneous center of rotation. And also, to us, you can take any point as virtual axis of rotation. But if you are doing so, please do so to do the adjustment. Self-rotation don't change, but the translation part introduce the angular momentum, which is mass times the velocity at the gravity center times the distance. What is this distance? This is the distance between the shorter distance between the gravity center, the shorter distance between the linear momentum passing through the gravity center to the virtual point of rotation. 所以你在算这个角动量的时候，如果是在叙述一个比较自由的运动 ，OK， 就不是绕着一个转轴转动，它可能是滚动，所以这个时候你要求的这个角动量随便你取，你取在重心。那你如果取不是在重心，你是取任意点，那你的任意点上面的角动量就来源这两个部分，一个是自转造成的，另外一个部分是公转造成的。Okay, so make sure you have that concept. Okay, so with this, now we can talk about the principle of impulse and momentum. Okay, you learn this linear impulse and momentum principle. If you multiply with the moment arm, then you're going to have an angular momentum plus the angular impulse. That is the moment integrations, time integration of moment. That will cause the angular momentum to change. Okay, so this is how it works. OK， 那我们那个具体比较复杂，我们就不讲，我们就直接讲你的这个例题。Okay, let's look at the example here. In the example here, you have a wheel. Imagine this is the wheel of your bicycle, of your motorbike. You can see that wheel is driven forward by the moment about the shaft. 所以你的轮胎转动，那主要就是因为你的这个轴上有一个扭力。Okay, in this case, you have it's definitely not your bicycle or motorcycle wheel. It is a 300 kilogram wheel that has a radius of gyration of 0.4 meter, and it is driven by a coupled moment of 300 Newton meter. Okay, that is very high. Okay, now you are asked to find what would be the angular speed after 6 seconds. It is start from rest and no slippage. Okay, in that case, so you just do the time integration, because if you care about the speed, okay, then and there is no change of potential energy. 所以例题上你要找速度，有两种情况可以找速度，一个是能量法，一个是冲量法或动量法。那这个例题你肉眼可看到的就是说它没有高度变化，所以你的这个能量法不大管用。那只是说你有一个扭力在，而且它还给你时间，扭力对时间的积分，你就得到角冲量，那角冲量就会造成角动量的变化。So in this case, so since you are given the starting impulse, starting momentum, the angular momentum, angular impulse, then that is causing you the angular momentum change. 那你有时候在解的时候，你要可以先画它的初始条件。那初始条件现在因为是滚动，所以你会有一个平移的速度，你也有一个转动的速度。然后中间有什么东西会造成这个速度变化？有重力，有摩擦力，正向力，也有扭力。And as a result of all this, then you're going to find out, then you're going to have your angular momentum chain. You also have a linear momentum chain. So this is the part that you have to draw. It is almost the same way as you draw the free body force diagram. I said now, all the free body force, all the forces are to be integrated with respect to time. And as a result, you have to add on the starting condition in terms of starting speed and then final speed, okay, both linear and angular. 好，你们画了这个图过后 ，OK， 那你怎么做？那第一件事就是说，因为毕竟牛顿方程这个还不足以满足你完全所知的这个情况，所以你要引用它的这个运动集合。So in the case of the wheel rolling, one very important thing is your gravity center is moving at the speed of radius times angular speed. Okay? So with this, now you can write your starting angular momentum plus the angular impulse is going to be a final angular momentum. Please expand the writing. If the wheel will start from rest, meaning the tangential, the translational speed was 0, angular speed was 0. So you got the starting 0 angular momentum. And then next, what is causing it to turn? Okay? You can do the integration with respect to the with respect to point A. Okay? You are talking about the moment passing through point A. That moment, okay? 所以同学你在解这道题的时候有一个前提， 所以你不要以为我们随便解。解这道题之前，请你看一下你要写的公式是什么。OK， 这个轮子，它不是，它是滚动的。So you have the point G, point A. You can write your equation, moment summation about gravity. Then that will be troublesome. You got the moment applied at the axis. At the same time, you have your this friction force times the radius. Okay. The other way of writing is moment summation about point A. So this is going to be the moment alone. All other point force, tangent, friction force is 0 moment arm. Normal force also 0 arm. And the weight also 0 arm. 为什么？因为你的正向力通过 A 点，你的重力也通过 A 点，你的摩擦力也通过 A 点，唯一没有通过的就是你的 moment， 所以这个非零，其他项都不见掉的。看到没有？你写这个公式，你是有前提的 ，OK？ 然后右手项怎么写 ？So what would you write on the right hand side? Because you are not writing the moment sum about the center. You're writing moment sum at point A. So it's going to be equal to I G alpha plus MVG times the moment arm. Okay? So because of this, if you do time integrations, okay, you are taking moment sum about point A. Doing the time integration will give you Ig omega 2 minus omega 1 plus m radius Vg1 Vg2 minus Vg1. OK， 所以你的这个动量的式子，角动量的式子，你的写法你是绕着 A 点在转动 ，OK？ 所以你不要以为你现在写的是什么动量守恒还是冲量动量原理，你还是要写你的牛顿方程。你要搞清楚你是拿哪一个牛顿方程去对时间做积分 ，OK？Then you will know, you will have no mistake writing these expressions, okay? And eventually, by substituting the value, then you are able to get omega 2, yeah, is equal to the applied moment times the times divided by your moment inertia. The moment inertia consists of two parts. One is for self-rotation, mk squared. What is mr squared? Mr squared is the orbiting introduced moment inertia. 所以你的这个转动惯量有两个部分，一个是自转的转动惯量，一个叫公转的转动惯量。Okay, so with this, then that we are done with the example. And then next, let's come to some of the exercise. So we'll start off with this. Yeah. Exercise 10. So I'll take the example of the aeroplane to illustrate the point. Okay? In this case, if you now have an aeroplane subjected to different thrust, okay? Okay, they have the turbine on the left hand side, they have turbine on the right hand side. The turbine on the right hand side is applying much greater force, it's 40 kilonewton, and then the one at the left hand side is subjected to 20 kilonewton. Okay, so if the aeroplane traveling at a constant speed, and then when suddenly the engine produces a difference in the thrust, right one is the TA, left one is the TB, and then can you find out what is the angular speed 5 seconds later? Okay, the plane has a mass of 200 megagram. Okay, so yeah, it's basically 200 tons. Okay, so if the radius of gyration of 15 meters, okay, what would be the case? So it's very simple. If you now take the axis of rotations to be above the gravity center, then you can immediately see that the difference in the right and the left thrust is causing you the angular acceleration. Okay? And what happens after 5 seconds? Just do the time integration of the moment, and then you will find that that moment is causing you to have self-rotation. So you can see that. So if it starts from no rotation, but after 5 seconds it ends with rotation omega, and that omega is the moment integration with respect to time divided by the moment of inertia. Okay, in this you can find that after 5 seconds you might have 1.02 degree difference. Okay, yeah. And then next we come to the question about the pulley and the weight lifting. So in this case, you basically have the two mass. You have the mass from the pulley, and then you have the mass from the load. So you are asked, if the double pulley consists of two wheels, which is attached one to another and turn at the same rate, the pulley has a mass of 15 kilogram and radius of gyration of 0.11 meter. If the block A has a mass of 40 kilogram, determine the speed of the block in 3 seconds after a constant force of 2 kilonewton is applied to the rod wrapping around the inner hub of the pulley. The block is originally at rest. Okay. So how do you apply the system? You can see pulley and the block as a separate system. But now, if you do a free body force diagram differently, you group them together. Okay? Then you can see how the momentum method generalized. Okay? You can see that what is the momentum change? Okay, there are two parts of the momentum. The first part is the momentum due to a rotating pulley. The second part of the momentum is due to the translation of the block. Okay? The two might not link up together, but later you see that. How do you describe the angular momentum? Okay, for such a system.
所以同学，你这个动力学这个部分很重要的就是你要能画出图来 ，OK， 啊，你能画出图来，你的答案就差不多在那边了。所以这个是滑轮，然后这个是一个块 A，OK， 然后你想想看，你滑轮在转动，那你这里上面的速度 VA 是什么？就是你的这个半径 VA equal to R omega，OK。那中间有什么 ？So what do you have in between? You might have the tension up, you might have the tension down, okay? And then next, you might have the work done. What's the work done? Work done by the force F, okay? Or in this case, it's writing the force P, okay? Force P are not applied at the same radius as the outer radius. So it is apply the inner one, okay, force P apply there. Okay, in this case then you have the radius Ri. Okay? Okay, what is the moment if you're going to write? If you're going to write moment sum, okay, you might have to write moment acting on the pulley. Okay, you have the moment about this point O, then you have your PRI, which is equal to what else? Not just PRI, you got the tension R. If it's outside, I write RO, it's going to I pulley alpha. Okay, so that's about the gravity center. Okay, then how about the equation next? The block A. Okay, the block A. The block A will have the tension. Okay, minus the weight is equal to my MA V AA. Okay, this is the two equation of motions. Okay, but the thing here is you can do time integrations. Okay, and block A part you can multiply the RO. So in this case, if you sum the two equations, then you can remove the tension. So that's the whole idea. So if you now do this, and now you do the moment sum, okay, then you can see that the tension is gone. What is left is the moment. This is the driving moment minus the load moment. If you group the two together， 所以刚才我是分而治之。那你现在你如果要把它全部包络在一起，也是可以的。所以你现在可能包络在一起的就是这个整个系统。那你外部看到的外力是什么？你外部看到的外力，一个是拉力，那外部看到的另外一个就是重力。OK， 那里面之间的这个内应力我就不管，你看没有？外部的拉力造成扭动 ，Ri， 然后外部的拉力造成扭动，乘上 Ro， 这两个得到的 moment， 它造成什么 ？So what does this cause? It causes the rotations of the pulley. Okay, because the pulley don't run away, pulley don't contribute to any translation-induced momentum. And then the one that run away is the block A. Block A is moving up and down. Then you have the block A velocity change times the mass of block A times the radius of rotation. Then you got your equation. Okay. With this, then you are able to solve for the angular speed change by doing the substitutions of the value in. And then if you sub in the value, on the third second what happens? On the third second you sub in the value, you can find that eventually you now have the angular speed to be 120 radian per second. It's quite fast. And then multiply with the radius of 0.2 meter, then you will find the block A is going up by 24.1 meter per second. So that's quite fast one. Okay, lastly, I come to the example here. Okay, this is the ball hitting a block. Okay, so what happened then? You can see it as 3 steps. The first step is the ball falling down, so the ball will gain in the speed. Okay, and the second is the ball hit on the rock. That will be the impact. And the third, if the ball starts together with the rock, they will rise together. Then that will be the energy chain. So let's look at the first step. For the first step, okay, you might easily find what is the ball landing speed, but it's on energy conservation. But next, what you want to determine next is your this impact with the rock, ball impact with the rock. Okay. If you are now putting the ball impact in you can see the ball is traveling down and do the hitting. And that hitting is causing the speed change. That speed change
is due to the impulse. Okay? So this is writing the equation for linear motion. So this is a linear impulse momentum chain for the ball. But to the rod, you can't write this that way because the rod is a rigid body that undergoes a rotation. Then you have to write the moment time integrations is causing the change in angular momentum. Okay? And what is this change of angular momentum? Okay, we can see that. Okay? So you can see these two equations. If we now do the sum, the moment acting on the rod is F times the radius times, if you do time integration, then you have to times time. That's the moment times integration. That is causing this rod to do the rotation. And this rotation happens to be off axis. So if you're writing this, you can write this as an expansion. That's the same writing. This is IB. Then you can write what is IB. Your IB is equal to a cell rotation plus the orbiting. So you're writing this. Times the distance. Okay. So just to let you know. Okay. Then you have to go and look for the distance away from the pivot. Okay. So this is the same. And then if you now do the time integration, if you aim to remove the internal impulse, because the action force is equal to reaction force, the impulse acting on the ball is going to be opposite to the impulse acting on the rod. So if you now do this, then you have the conservation of the momentum. Okay? So after you have the impact, after you have the speed after the impact, then you can find out what is the energy change, because the speed will be converted into potential energy. Okay, with this then we are done. And also, just a recap on the energy method, if you haven't gone through. A quick recap. Okay, in this case, this is a ball hitched to this is a wheel hitched to a spring. So in this case, you can see the energy coming from two parts. Kinetic energy can come from the self-rotations, and kinetic energy can come from the translation. Okay, so that's the key thing you have to take note. And how does it work? Okay, if you now have a wheel rotating by the angular moment, but now if you hitch onto a spring, the spring will provide the resistance linearly. The moment will provide the angular rotation. Okay? The work done by the moment is what we call moments times angle. The work done by the spring is half kx squared. Since moment m is the driving one, it's doing the positive work, but the spring is opposing the forward motion, then this is the negative work. So together, that work done is causing you this change in the kinetic energy. So this is you need to know. And then next, if you now have a big rod BD on the support by master's rod AB and CD. So what are you going to write for this? 所以这一题，请问 BD 有没有自转？没有。Okay. In this case, when you're writing the equations for the energy, yeah, you have to be clear. Okay. The BD is only contributing to translational kinetic energy. There is no self-rotation. Self-rotation happens to only the rod AB and rod CD. If these two are equal, then they form the parallel mechanism. So the kinetic energy to write this is now only translation part from BD, rotational part for this A and C. Okay. And then next, what is driving it to rotate? It is because of the leaning down. So the weight BD is coming down in height. The gravity center of AB and gravity center of CD is also coming down. So in the end, it's the gravity work done that caused the speed change. OK， 那细节我就不讲。然后但是这个 BD 这个杆 AB 跟杆 DC， 因为它的质量中心是远离转动点，所以它质量中心它的转动惯量有2个成分，一个叫公转，一个叫自转。OK， 所以它不是简单的这个 IG omega square， 它还要加上它自己的这个 MVG 平方。Okay, so and then last, this is the example similar. As I mentioned to you, momentum method can give you some result. Okay, and this energy method can also give you some result. But it depends which method to work, depends on you. Okay, in this case, because the moment, the change of the height is due to the weight, this is purely the gravitational potential energy change. So you can use the energy method. And some more, the most important thing when you want to use the energy method is you want to find the displacement. 当你要找这个位置变化的时候，公原理会好过你的冲量原理。Okay, and lastly, come to the example here. Yeah, you go back. This is the same as your experiment done. So this is a two bar coming down under its own weight. So you can see that starting from 60 degrees, okay, then they come to 0 degree. Essentially, it is the height chain of rod AB and height chain of the rod BD. Okay, they come down by a height. Okay, eventually, starting from rest, they end with the velocity VB. But VB is not the one that you calculate the kinetic energy. You need the VG. Okay? So what you do to find the gravity velocity at the end? So you might see from the constraint, because of vertical symmetry, VB can only go down. And then VC can only go horizontal. And then if you draw the instantaneous center by drawing out the radius perpendicular to VB, radius perpendicular to VC, you can find the RB equal to L. And what is your RC? 来，欧洲同学刚刚做的 RC 是多少？在这个位置。画法线 ，RC 是0。OK， 所以这个点在末端就不动了。OK， 所以你要能从图上面顺心画出你的 RBRC。OK， 那你画完 RBRC 也没用，因为你现在要找的是你的，如果要找动能，你就要找到你的重心的速度。OK， 你才能写出动能。动能不是靠你这个 VB， 也不是靠你 VC 找出来的，它是靠你的 VG。So how do you find your VG? Okay, the right way to write VG. Okay, it's almost like the parts of the gear. The VG can be written as VC plus VGC. Look at here. Because VC, radius RC is 0, VC is 0. And so now you have the G relative to C motion. This is a rotation. This rotation is L over 2 times omega. Okay? Now
you can write Vg is equal to L over 2. That is on the condition, yeah, it is 0. And then next, your this Vg in terms of Vb, they also have 0, they also have, but they have non-zero Vb. But because the moment arm is negative, it's negative L over 2, then you're still going to get the Vg equal to L over 2 omega. OK， 所以这个公式啊，同学你要自己去画一下这个速度三角形图，它不是用背的，它是从几何上得到的。OK， so with this, now we can go and calculate what is the kinetic energy for the rod AB and kinetic energy for the rod BC. And now, yeah, then you can calculate how much the work done, causing how much the kinetic energy change. Yeah, with this, then we are done for today. Thank you for your attention. And examinations on the Thursday will cover the topic of momentum for particle, rigid body kinetics, rigid body kinematics, rigid body impulse, and energy method all together. OK， 好，那我们周四见。OK， 好，考试顺利。